That's unique.
Miraculous. No, and
It's I've never heard that joke before, so I appreciate that.
It's tied up by the chain. And then also
All right, we're gonna move on now because we have a finite amount of time and yeah.
Sharing that, though.
All right. So to do today, our plan: we're gonna go over homework. I can answer whatever questions you have if there are some, and then we're just gonna keep moving forward in the energy conversation. Really, is what we're doing. We've got some problems to work. We've got some things, and we'll just kind of go as far as we do or need to or whatever, and we'll keep cruising. All right. So. First situation is homework questions, if there are some.
I got confused on what we were supposed to do exactly.
Okay.
We finished the first one and then did the second one, right? Or there was
Say this again?
There were the 2 questions from the one we went over yesterday.
Okay.
That we were supposed to finish, right?
Maybe, I don't remember. Sure. These are the ones that I had intended that you would do.
Okay, well.
And maybe that happened or maybe it didn't. I don't know. Ian's got 25.
Okay, I didn't, yeah.
Is that okay?
Yes.
Okay. So here we go. Question number 25, again from chapter 10. We'll go back there. 25. Are these?
25?
Oh, I was looking at 23. I was really confused. Okay. It's like I read 23 and didn't like it. 25 makes more sense, though. Okay. A roller coaster, bless you, starts from rest at its highest point and then descends on a frictionless track. Its speed is 30 meters per second when it reaches ground level. Oh, yes. This is like classic AP Physics 1 question. That's why I picked it, because it's good. So let's do it. So 25. So we've got, also I love roller coasters, so there's that too. All right. So this is our h equals 0 point. We're going to start up here with a velocity of 0. It says that its speed when it's down here at the bottom is 30 meters per second. What is the speed when its height, what was its speed when its height was half of its starting height? Okay. So here's h, and this is h over 2. And we want to know the velocity there. How are we going to do that? Stare at it for a little while. Squint, wiggle your head. If that doesn't work, and sometimes Courtney's saying that doesn't always work for her. So let's take a look at what we know. Let's take a look at this. We're actually going to use some of the skills that we're going to learn today to talk about this. Let's talk about its kinetic energy. Oops, I'm just going to call that K. Sorry. I taught for many a year where it was KE. And U sub G at each of these places. K and U sub G and K. What is my problem? And U sub G at each of these places. All right. Does the cart have any kinetic energy at the top?
No.
Gunnar, you were shaking your head. Why did you say no?
It's not moving, and that's the beginning of where it starts.
Right. It told us that the velocity here was 0, didn't it? So the kinetic energy here is 0. Does it have any gravitational potential energy there? Yeah. In fact, if we're only talking about those 2 kinds of mechanical energy, remember at the end of yesterday we said that all of the energy has to be the same at the beginning and the end. It's that whole idea of conservation. We talked about conservation of momentum. In chemistry, we talk about conservation of mass. And in all sciences, we talk about conservation of energy. So we've got 0 kinetic energy here. And I'm just going to say it's all potential here for now. Is that okay? I don't know how much it is, but I'm going to say all of it is potential. What about down at the bottom?
All kinetic.
Why is it all kinetic?
Is that 0?
Because what's at 0?
The card is at h equals 0.
The cart is at h equals 0. We're going to remind ourselves that the potential energy gravitational is mgh. So Isaac was taking a bunch of steps at once and he said, hey, H equals 0. So that means that the gravitational potential energy is 0, which means that the kinetic energy has to be all, right? All of it has to be kinetic energy now. Because again, we're assuming for right now, said it was frictionless and we're assuming no air resistance and all of that business. So we got all of it here. What about at this place here?
It's in between.
It's in between. Yeah. So I agree. Absolutely, it is in between. Can you be more specific? I just it looked like I don't know what you were doing. Anyway, all right. So it's in between. How much in between? Do we know?
Just say halfway.
Halfway.
That doesn't sound very convincing, though. Can you convince me that it's halfway? If you really think it is.
Well,
That has nothing to do
we don't know
with
what promise. Well, H over 2 reveals something. Oh, I thought that's what we just. Oh.
This is MGH, right? That's total big old H, right? What's the H here, Grace?
H over 2.
It's H over 2, right? So this is H over 2, so this is mg times H over 2. Hey, hot diggity, you could write that as mgh over 2, right? So half of the energy is in potential, half of it is in kinetic there. Is that okay so far? Okay. So I'm just kind of like trying to think this through because, you know, it matters. So here we go. So we're going to say half of the total is kinetic here, and half of the total is potential. So maybe that tells us something. What's up?
Is that because it's at halfway?
Indeed. Yeah, because H over 2 is our height. So that would be like mgh, which is up here, right? Divided by 2, half of it. Yeah. Okay, so what about that? What's the question? Roller coaster starts from rest at its highest point. Its speed, oh, by the way, let's just write that down. The velocity here is 30 meters per second. Okay. And so how fast is it going to be going up here? Don't be tempted to say that, right? Why do you want to say 15?
Because it's H over 2.
Because it's H over 2, for sure. But why does my gut say that's not the right choice?
Because it's probably going really fast. Because
What's the equation for kinetic energy?
one half
M
VT or
V squared. What's that? What's up with that squared? Are you with me there? Yeah, go ahead.
Also, the kinetic energy formula isn't impacted by the height.
First,
Compared to the potential energy.
that's true. So let me ask. So you said the kinetic energy formula is not dependent on the height. So are you advocating then? I just want to make sure, like I want to see where your head is taking us. Are you saying then that the velocity should be 30 here as well?
Not necessarily. I'm just saying it's already not 15.
Okay, like you just don't like that half inclination. I will tell you that a lot of people want it to be a half, right?
Yep.
Yeah.
Halfway. It makes sense for it to be half, right? The reason I love this problem is because we have good conversation involved. So at the bottom, and I'm trying to do this without like plugging in numbers because I want to see if we can stretch our brains a little bit on a Friday afternoon. So at the bottom, we've got K is equal to 1/2 M times that 30 squared, right? At the top, or excuse me, halfway, I'm going to call this K sub 1/2, K halfway, and I'll call this K at the bottom. Is that okay that I'm doing that? I'm just putting some subscripts so I don't get confused. So this is the K at the bottom, the potential, or excuse me, the kinetic energy at the bottom. This is the kinetic energy halfway down. The kinetic energy halfway down is going to be half of this. Are you with me there? Because this is the total, because you told me it's all kinetic down here. You okay with that? So it's going to be half of this business. I'm just kind of playing with this to see what's going to happen. So it's going to be 1/2 M times 30 squared divided by 2. Is that okay? Yeah, because it's half of it, is equal to the K at the bottom. And I'm just going to kind of write this down. 1/2 M. Oops. This velocity here squared. Velocity at the 1/2 point. I should have labeled that a different letter. That would have been better. Sorry. I don't have this like all memorized. I just kind of do it because that's how I teach. So I apologize if that seems confusing. So this is at the top. This is halfway down, and this is at the bottom. The total kinetic energy halfway down is half of the total kinetic energy that we have. And that's equal to 1/2 mv, the velocity there, squared. There are m's on both of these. Yes or no?
Wait, how is it equal? Because it's just the same thing.
Here. I feel like I'm leading you down a rabbit hole that you don't want to go down. You're like, no, don't do it. Don't listen to that part of the video because it's going to be really loud and scary. Watch out for that. This is the total. That yellow stuff is the total kinetic energy at the bottom. Yes or no? Yes?
Yeah.
Okay.
But it's half, so you take it over 2.
Yeah.
I know that.
This is the total kinetic energy at this halfway point.
So what's that?
Again, the reason I like this, the reason I want to look at it is, are there anything similar on both sides of this both sides of the equal sign? They're halves and halves. So can I get rid of that half and half? And also what? So 30 squared divided by 2 is equal to V half squared. What's the velocity of this thing going to be? What's that?
It's like 21.21.
21.21, right?
I know the answer is 21 because I did that.
But you can't do that on a test, which is why we got to figure out how to get there.
Because I
So,
thought I
yeah.
knew the answer, and obviously.
It wasn't 15.
No,
Yeah.
I figured it couldn't be 15 because it wouldn't have 2 bars if it was 15.
Wouldn't have 2 bars.
It has like the level of difficulty next
Oh.
to the question. That would be like a half
Clever.
bar.
Clever. So we can plug this in. Kian tells us it's 21 point something something. Yeah?
Yeah.
Okay.
Square root of that.
30 squared, right?
It's not.
Multiply it by 2.
It's just the 30 squared. Then divide that whole thing by 2.
So KB is equal to that yellow part.
21.2.
Ask me your question one more time.
KB is equal to that yellow part.
KB. Yes. Yes.
Then where did the 2 come from? You divide it by
Because I'm a halfway down. Half of its potential, half of its kinetic. We're going to do more of this in just a minute too.
This total K at bottom.
That's bottom all kinetic.
You said it was halfway.
This is halfway. This is at the bottom.
So I'd say half of it.
So it should be 50.
You got it.
Yeah. Yeah. Let's do more.
Let's do 20 or 35.
Which one?
35.
20 first? Let's do 20 and then we'll go back to 35. Is that okay? We'll stick with the questions first. All right. Sandy and Christian on the edge of a cliff and throw identical mass rocks at the same speed. Hey, we did this a long time ago, didn't we? People throwing rocks off of cliffs? That was like October or something. Okay. So the funny thing about this, you guys, we did all that projectile motion business, but it's so much easier with energy. Sandy throws her rock horizontally while Chris throws his upward at an angle of 45 degrees to the horizontal. Are the rocks moving the same speed when they hit the ground? Or is one moving faster? If one is moving faster, which one? So you've got one that goes like this, and you've got one that goes like that, right? Whoa, that was really ugly. Sorry about that. Is that right? Does that look about right? Something like that.
Yeah.
Which one's moving faster at the bottom?
The
They're the same.
So here's my rock in both cases. Can you calculate the potential energy? Oops. Given the height? Yeah. So at the beginning, the initial oh my gosh, I'm sorry. I've indoctrinated myself and now I've got to get out of it. Initial potential energy plus initial kinetic energy has to equal the final plus the final, right? That is conservation of mechanical energy. Boom, right there. How does the potential at the beginning compare for the two rocks? Same, mgh, right? Same mass, same g, same h. How do the kinetic energies compare? Same 1/2, same m, same v squared. So the total energy at the beginning, same, equals the total energy at the end. How much potential energy do they each have at the end? How much? If I call this h equals 0.
Oh, 0.
0. So that goes away. So how do their kinetic energies compare at the bottom? They're the same. And if they have the same mass and they have the same 1/2, then their V's have to be the same. They have to be equal. Yeah. They'll land at the same speed. Yeah.
So that's like the same thing with the balls.
That's what I
like
said.
that.
Yeah. Sweet, sweet.
We're
We're learning things, right? It's good. Are we okay with number 20? What was the other one? 35? All right. We're going to do one more. So just so that everybody knows where we're at, we're doing problem 35. That's what you requested, right, Kate? Is that true, or was I dreaming? Or did somebody request that?
I requested.
Oh, okay. I'm sorry. Isaac requested it. I apologize. I thought that just, yeah. Getting mixed up here. A boy reaches out of a window and tosses a ball straight up with a speed of 10 meters per second. The ball is 20 meters above the ground as he releases it. Use conservation of energy to find. Oh, these are fun things. Okay, so reaching out a window. So there's the building and there's the window opening. Right? And so the ball is going to be, is it thrown, tosses it straight up in the air. So it's got an initial velocity in this direction. It is 20 meters above the ground. There's the ground. Okay. Is this making sense? Is my picture okay? It's kind of...
Can you walk me through one more time?
Yeah. This is the window. This is the building.
Yeah.
The window's opening. He's going to throw the ball in the air. The ball starts 20 meters above the ground. Is that okay? Thanks for asking for clarification. I appreciate that. Okay. Initial speed was 10 meters per second. The ball's maximum height above the ground. The ball's speed as it passes the window on the way down. The speed of the impact. We've totally got this. Easy, easy, we got this. The whole principle, friends, is that the potential energy plus the kinetic energy at any 2 points, I'm going to label this as the top, plus the kinetic energy at the top has to equal the potential energy at the end, plus the kinetic energy at the end. It's always, 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 always going to be the same, assuming there's no air resistance. Right? So at the beginning, does the ball have potential energy?
Yeah.
Mm-hmm. Does the ball have kinetic energy? By does it have kinetic energy? I mean, really mean, is it moving, right? And absolutely it is moving. So it's got both. Yes. So we could calculate the amount of that, I think. What number are we doing? I just lost it. 35. There it is. Okay. We want to know how high it's going to go. When it gets to the top, when it gets up here to the top, to this place where we're going to call the top, what do we know about the kinetic energy at the top? What happens at the very top in terms of its velocity?
It stops moving.
It stops, so its kinetic energy is 0, right? So at the very top, we've got just potential energy. And at the very bottom, what's interesting? I heard some mumbles, but I didn't hear an answer.
Potential is 0.
Potential is 0. How are we doing? Are we okay? Just writing some stuff down. Writing down what I know. So I've got the initial situation. I've got M times G times a height of, I'm just going to put in the 20. And I've got 1/2 M times that 10 squared. I'm going to put my units in there too because I want to be a good kid. So that is at the very beginning. At the top, that's equal to M times G times the height at the top. Is it bothering anybody that it doesn't tell you the mass?
Yeah.
For some people, it's like, that is really disturbing because I'm trying to use energy to solve this problem. But then you look at what we have written down there, and what do you notice about every single term?
There's an M in it.
It has an M in it! If there's an M in every single term, what happens to the M?
Cancel out.
Bye-bye! Catch you later!
See you later.
Adios! Bye-bye! Now, before we actually do the math, I want to point out to you, we have done this problem so many times. You did this problem at the end of September because I had the frog and I told you that I threw him in the air with an initial velocity of something, and I asked you how high he went. You did this problem. We could go back and we could watch the video of it. Okay? Do you remember doing that?
Yes.
When we did that, did I tell you anything about his mass?
No.
No, we didn't mention the word mass until like the 6th week of school or something, right? Like just because we thought it might be interesting. Okay? So this is all kinematics. Watch what's going to happen. I've got a G times a D, right? So an acceleration times a distance. And I've got a velocity squared. This is just the kinematics equations, you guys. This is just the kinematics equations with the mass is taken out. Okay? I just want to point out to you that mass does not matter in a problem like this. We don't need it. I don't know what to do with my thing.
What is
I'm going to leave it alone because it's a different problem. It's a different part of the problem. By that I mean, let me back up and tell you what I'm trying to say here. Part A asks how high it goes, right? If I only want to know how high it goes, I don't care about when it falls. All I care about is the process from here to here. Does that make sense? Who cares about when it falls? Not me. All I care about is this. That's where it goes. Yeah. Very, very good question, though. So how do we do what?
How do we find that equation?
Yeah. Because you know G, right? And you know everything else. So you could solve for that. Sure, as long as you keep it negative everywhere. But I
For this problem?
for this problem it would be okay.
Oh, yeah, you can get rid of G, can't you?
I would always use G as positive. In these
No.
things.
You can get rid of G.
No, because there's no G here.
Once you combine them.
You have a term with a G and a term without a G and a term with a G.
Right.
So you can't get rid of G. Make the G positive. Use 9.8. Right? Do you want something different?
No. Yes. No. I just heard the music.
I never one asked.
Oh, you can. That's fine. Hey, quick question. Let's do part B. Part B says how fast is it going when it passes the window? when the little boy waves at the ball as it's falling back down? What's that?
There's a very, very similar.
You probably did. How fast is it going? Yeah. Yeah. Because you've got U sub G plus Ki equals U sub G at that as it's coming back down plus Ki or K, right? MGH plus 1/2 MV squared. MGH plus 1/2 MV squared. How do the heights compare here? The height when it's here versus the height when it's here.
It's the same.
Same height. So that means this goes away. So how do the velocities have to compare?
Gotta be the same.
They've got to be the same. They've got to be the same. So that's the speed. Does it ask for the speed? It does, because we don't care about the direction now. We would say it's negative, but I'm not going to worry about that. All right, Kate really wants to do this final part. I know she does. She's like, what about that final kinetic energy? So let's do it here. So that one says the speed upon impact on the ground. So you've got your mg times 20. This is from the initial, plus 1/2 m times 10 squared is equal to, now it's just 1/2 m v final squared. Hey, look, there's an m in everything.
You know what that means?
I do know what that means. Do you know what that means?
Yes.
Good. So glad.
Wait, is that an R?
Oh, yeah.
Can you read? That's an F.
I don't know what you're talking
Are you talking about here?
No, above.
That's a V.
It says 1/2 times R squared.
It's VS squared. Dude, what is R?
Oh, radius.
Gradient.
Hey, nobody that much was probably
No, he's getting confused with momentum.
Stop, please. I'm trying to take this.
Ellie, I think you're awesome. All right. How are we doing, team?
Leave it up there for a hot second.
I'm not going anywhere.
So A and C are the same, just different parts.
Yeah, what's the answer? Nah, it's 0.13.
It's 120.
Oh,
Oh, and that's square root.
So B is 76%.
I'm right.
1/10. 11.
490. Supposed to be a third. No, I got 490.
Did you get what? Do you know what it was?
No, I don't. I mean, I could do it if you need me to. All right. I'm ready to keep cruising. Are you guys ready?
Never mind, you're right.
Everybody happy?
Yeah.
Here we go.
I've got the 5.
So I'm going to introduce a new concept to you. So put that homework wherever it goes or turn to the next page or whatever. We've kind of danced around this conservation of energy stuff, which is absolutely fine. But I want to teach you a skill to understanding conservation of energy that I kind of alluded to, but I didn't want to like throw it into the homework because that seemed a little confusing. Okay. The concept is, so I'm going to tell you what it's called first, and then I'm going to let me tell you a little story about it. So there are many different philosophies about teaching physics. Okay, and I don't know if you guys have friends who are taking physics at West and at City, and if you've ever talked to them about how the teaching goes. But there are different philosophies, and different teachers do different types of approaches. And there's an approach that is used by some of my colleagues that I've been introduced to a number of times, and every time that I'm introduced to it, I'm like, oh, I just don't know. Like, I just don't know if that's something that is like in my belief system as a teacher. And I've kind of fought it, and been okay with it. Like I feel like I do a pretty decent job. This falls out of that category. This is something that comes from the philosophy that I don't like ascribe to mostly, but I have learned over the past few years is very, very powerful. The reason that I'm telling you this is because when I was first introduced to this, I'm like, this is really dumb. Like, why do I need to do this? My students are way smarter than that. Like, they don't need this. Do you understand what I'm saying? Yeah. So I don't want you to be like, why is she teaching us this? This is dumb. Because I felt that I learned it. And then as I worked through it, I'm like, oh, it actually does some cool stuff. Like, you can actually really understand physics by doing it. So that's why I'm doing this. I always want to tell people that because I don't want to be apologetic for it because I think it's important, but I also don't want you to think that I'm dumbing things down for you. Okay? So energy bar charts. Here's the concept. Is that you're going to make literally a bar chart with different kinds of energy. Now, so far and today, we only have 2 kinds of energy. But throughout this unit, we're going to add more kinds of energy, and we will build up these bar charts into bigger and better things. But for right now, we've just got our 2 kinds of energy. What and what?
Kinetic and gravitational potential.
You got it. We've got kinetic, and we got U sub G. And so the concept is that as a system passes through different parts or from different one situation to another, the total amount of energy needs to stay constant, but the type of energy that it is can change. So we're going to drop a frog again because that's, what we do. And we're going to look at the kinds of energy that this frog has at multiple points throughout the story. Okay? So at the beginning, so you're going to have to do a little bit of math here because I'm going to tell you the mass of my frog. I'm going to tell you that the frog has a mass of 1.2, I'm just kind of making this up, kilograms. Okay? And I'm going to hold the frog up here. How high is this? I don't know. 1.8 meters above the ground, we'll say. Okay. And I would like you to determine for me how much potential energy and how much kinetic energy does my frog have? Can you do that? Go ahead and do that. Talk to each other, have a little conversation, figure out how much it is.
My name's Trey, and I got
Rudy, do you need a calculator? I can let you borrow a calculator. Here's a calculator. It's true.
Yeah.
All right. You guys doing okay?
Wait, Carolyn, are we going to use 10 on the exam or 9?
I think you can use either one. I think as long as you're explicit, it doesn't matter. I think that the general consensus in the room is that we're going to use 9.8. So if you want to compare your answers to them, then I would use 9.8.
9.81.
I don't know. What do you guys want to use?
I don't know.
9.81.
I used
9.81. Okay.
9.8.
Oh my gosh. 9.8? Yes?
9.81.
I know. I'll fix it. Just chill.
Which one is it? That's what I'll use.
We're going to use 9.81. Class decision.
Yes.
Oh, we
I know.
get it. 1.
Wow. All right. Henry, did you figure out how much kinetic energy the frog has at the top?
0.
0. So how am I going to mark that on my bar chart? Well, that's pretty darn easy. It's at 0. Brianna, did you figure out how much potential energy the froggy has? Oh. Liam, did you figure it out? Or did somebody figure it out? How much potential energy does the froggy have?
1.2.
Oh, didn't we say the height? We said a height, didn't we?
That's 1.8 meters.
21.19.
Okay, we're just going to call it 21. Is that okay?
Wait, 22.
Oh, 22?
No.
Wait, no.
21.18.
21.
Yeah. 22.
You're not dumb.
No, yeah. Oh, yeah, that's all right. This is like
All right. There's your energy bar chart. It's kind of cute, right?
I like it.
All right. Now we're going to let the frog drop. It's pretty exciting. All right. Let's do just the bottom.
Who's that?
I know, right? He's well trained. At the bottom, go ahead and draw that energy bar chart. You got this. The bottom, yep. So this is at the top.
Now we're down to the halfway mark.
Nope. At the floor. Before the force of the floor stops him. Because otherwise we have to include heat. I don't want to do that yet. Soon, but not yet.
Yeah, I was like,
What's it going to look like, friends? This one, this is the power of this right here. How much potential energy do we have?
0.
0. How much kinetic energy do we have? It's before the force of the floor applies. Otherwise, we have to have heat, and we're not going to do that yet. We'll do that next week. So we'll get there. We're just not there quite yet. Somebody have a question? So we're just going to do this real quick here. We'll say at a height of, I don't know, 0.67 meters. Can you make a bar chart for me? An energy bar chart to describe the kinetic and potential energy at 0.67 meters?
Yes. Yes, I can.
Really?
This one.
Figure out. Yeah, wait, isn't it 21? I was wrong.
Oh, it is 21. I stopped listening to you. Do you need to know the velocity of the frog? Sorry, that Harrison was saying 22 and he shouldn't have been.
Yeah, I was bad.
Yeah.
I know, right?
Yeah, he got
We
me
was
too.
right.
You have an eraser. Oh, you don't? Oh, friend, I don't know what to tell you then. Sorry.
I know.
How much potential energy does that froggy have?
Like 7.9.
7 point something something?
How about 8?
I had 8.
8?
Well, it's
You guys used your number
8,
8 or not?
but
You guys are so whiny.
yeah.
If it is 8, approximately, how much kinetic energy does the frog have?
minus 8.
Right. See, that's nice, right? Boom and boom, you're done. 21 minus 8, which is what? I don't know. These things always have to add up, don't they?
Yeah.
Always and forever. It will get more interesting as we go. I don't want to go too far into that right now. I do want to do one more problem before the end of the day, so I'm going to throw it
Wait, so
here and just. Oh yeah, go ahead. Sorry.
So that's okay. Obviously, I know that they have to be opposite, like at the top and at the bottom. But without that, how do you get that? Like if you don't know the velocity.
I think you're right.
Friends, I would really appreciate if you guys could be quiet. First of all, because probably others of you need to hear this question, and secondly, just because it's rude to talk when other people are talking. Say that one more time. I'm sorry.
Okay. So I just know that K and potential have to be opposite at
Yes.
the top and the bottom.
Yes.
We know that, but other than that, how do you find K without the velocity?
You don't. So
You don't?
well,
So you just
the
use
game is that anytime the total amount of energy has to be the same.
Okay.
So we always have to add up to 21. So as long as you know it one place, you've got it.
Okay.
Is that making sense?
Yeah.
Does that answer the question you're asking me though, or no?
So you just don't need to find it.
You don't need to.
Okay.
Yeah. So this is the nice empowering opportunity here, right? That you don't need to know the velocity all the time. You can still tell me things about the system without having to deal with any of that other business.
Okay.
Does that get where you're going? Okay, cool. All right, I've got one more for you today. I think this is it. This one's kind of similar to the one that we did at the very beginning in your homework, but it's kind of the opposite question. So I want you to take a look at it. Assuming the height of the hill in the figure is 40 meters, so this is the top hill here, okay, y equals 40. Bless you. And the roller coaster starts from rest at the top. Calculate the speed of the roller coaster at the bottom of the hill, okay? And at what height will it have half of this speed? Okay? So you're kind of doing the same thing in reverse using conservation of energy. It doesn't tell you the mass, but we're okay, right?
Yep.
Okay. I'm gonna let you guys work for a little bit. Is that okay? There's some good stuff in there. You got this.